Okay. Hello guys. Let me know if you guys can hear me. So, or let me check myself only if I can hear myself. Yep. I think I'm audible. So yes, let's start with the problem for the day. So the problem for the day, like it was yesterday's problem. The problem was merge case sorted linked lists, right? So I think the problem name itself actually tells you what you have to do. You are given case sorted linked lists and you have to merge them. What do we mean by merge them? You do not merge them in a random way. The merged linked list, that is after merging them, the linked list that you get, it should be also be sorted order, right? It should also be in sorted order. So you're given case sorted linked lists of different sizes. The task is to merge them in such a way that after merging they will be single sorted linked list, right? It will be a single sorted linked list. So for example, if we take k equals to 4, there are k linked lists with us, and the values of the linked lists are 1 to 3. The first linked list is 1 to 3. It's a sorted linked list. The second one is 4 5. Third linked list is 5 6, and fourth is 7 8, right? So if we merge them together and have a sorted linked list, it will be 1 2 3 4 5 5 6 7 8, right? So it's a sorted linked list that is formed by merging all the four linked lists. So that is the question, and we'll see how we can solve this. Similarly, for the second example also, you can see that 1 3 4 5 6 and 8, these are the three linked lists. After merging them, what should be the sorted linked list? 1 3 4 5 6 8, right? So that should be the sorted linked list. So this is the question. How can we solve this? Let's look into that. Okay, so there are actually multiple ways we can do this. There are multiple solutions possible for this. But again, like if we look into what are the constraints that are given to us, or what is the complexity that is expected, we see that it's n into k into log k for time complexity, and auxiliary space complexity should be order of k. Okay, so additional space complexity we can take is order of k. Okay, so first idea is, sorry, I think I have to escape here. Yep. Okay, so the first idea will be that there are multiple ways, right? There's a brute force way where you can go through all the elements one by one, and rather you can actually combine all of them in an array and then sort it and then create a linked list out of it. It's a brute force method, but that will definitely not be the solution that we'll do. We can do it much better way. One way, I'll not actually write the code for this, although this is the optimal way of doing, but again, I'll not write the code because the space complexity will be higher than the actual solution. But again, like this is a very interesting way and this is a very intuitive way, I would say. And you can definitely, like if this is asked on your interview question, you can definitely try this way as well, and I'm pretty sure the interviewer will be happy as well. So the idea is that we can use a divide and conquer based approach, right? So we have linked lists, right? We have linked lists. So linked list 1, linked list 2, linked list 3, like this linked list n, right? So what do we do is we divide the linked list into two sets, right? So first set will combine them like this. So L by 2, first L by 2 linked lists, L1, L2, L3, L4, and here it will up to Ln by 2, and here it will be Ln by 2 plus 1, then like that, and up to Ln, right? The second half, like this will continue breaking until we have two linked lists, right? So L1, L2, L3, L4, like this. So when we have two linked lists, we can easily merge them together. We can easily merge two sorted linked lists together. So we'll merge them and then we'll build up. So this was coming from L1, L2, L3, L4, right? So L3, L4. So this actually resulted in a single sorted linked list, right? This gives a single sorted linked list. L3, L4 again gives a single sorted linked list, right? So you can now merge these two linked lists together and form a single sorted linked list. So this is one of the ways we can do it, and this is a pretty good way actually. Like you can definitely try this way out. Just give me a second. Okay, so you can definitely try this way out. Let me actually give another example so that you understand it properly. And we'll take a small number of linked lists, right? We'll not take a general n linked list. We'll take some of the some linked list, right? So let's do something like this. That let's say we have four linked lists, right? L1, L2, L3, L4. We have four linked lists. First, we can divide this into two linked lists, L1, L2. and this into two linked lists, L3, L4. So we are going for a divide and conquer based approach. We are dividing and then conquering. So this is similar to the merge sort algorithm that we do as well. So L1, L2, now we can have a method that will merge two linked lists, right? So merge two linked list, LL. So it will take two linked lists and it will merge them, right? It will merge them into a single linked list. We can easily do this, right? It's very similar to the merge operation in the merge sort algorithm. So we are able to merge these two linked lists. So this now returns a single linked list, right? So let's call it L12, and this will return a single linked list. Let's call it L34, right? So now here, when we come to this level, what do we have? We have two linked lists, L12 and L34, which are sorted, and we have to merge them together. So basically we'll call the merge 2LL with L12 and L34. So what do we get out of them? We get L1234, that is the entire linked list merged sorted linked list. So this is definitely one way we can do this. You can definitely try to write the code for this, as it is pretty interesting, but we'll go for a better solution, right? We'll go for a better solution. By the way, the time complexity for this will actually meet. It will be n into k into log k. The space complexity, however, will be n into k. But we can have a order of k space complexity as well. So let's look into that. How can we do that? So let's take an example of a linked list, of few linked lists. So L1, let's say 1, 2, 5, 6, right? Then we have L2, it will be, let's say, 3, 4, 4, 5, right? Let's say we have L3, it will be 5, 7, 8, 10. And we have L4, which will be 1, 6, 9, 10, right? We have like this. We have the linked lists like this. And we have to combine them into a single sorted linked list. What can we do? Okay, first of all, we'll take a priority queue, right? We'll take a priority queue or a heap, min heap, basically. Why do we need a min heap? Because we can always extract the minimum element out every time, right? So we'll make a min heap out of them. First of all, we'll not insert all the elements. We can definitely insert all the elements and then pull up one by one, but that will increase the complexity. So we will not insert all the elements. In the min heap, let's call it PQ. In the min heap, we can just insert the first element of each of the linked list. First element of each of the linked list. So 1, 3, 5, 1. First of all, we have 1, 3, 5, 1 in our priority queue or the min heap, right? After that, at every step, what do we do is we extract the minimum element out. That is, what is the minimum element in this priority queue? It is 1, right? So we'll extract 1 out. So 1 is extracted out. Let's say this 1 is extracted out. Now, when we extract this out, we'll definitely add it to our answer because this is a smaller one. But at the same time, we also do one more thing, that is we will push the next element of 1 into the priority queue. And why does this work actually? This works because 1 is, this linked list itself is sorted, right? So definitely 1 is smaller than the next element that is there. So 1 will come before the next element. So when we enter the next element, we are pulling out 1, right? We are pulling out 1. So we definitely know that all other elements that are there in the linked list will be greater than 1. It will not greater than equal to 1. It will not be less than 1, right? And now we can safely push 2 because 2 is definitely greater than 1 because each linked list is sorted. Now when we push 2, as it is a min heap, it will automatically reorder itself with respect to the sorted value. So we are pushing 2 here, right? Now what is the minimum element again? What is the minimum element again? It's 1, right? So once we are done with one of them, let's just mark where are we at every point. So for this linked list, we are at this point. For this one, we are here. For this one, we are here. And for this one, we are here. Now we again have a 1, which is this one, right? So we'll remove this 1 from the linked list. We'll add it to our answer linked list, 1. And we'll push the next element, that is 6. So 6 is pushed into the linked list and we move one step. We have moved one step ahead, right? So we have moved one step ahead. So we come here. Okay. After this, what do we do? What is the minimum element in the linked list? In the priority queue, it's 2, right? This 2. So this 2 will be added to our answer linked list, and we will remove this 2 from the priority queue and we'll insert the next element, that is 5. Why are we inserting 5 now? Because we are sure that 5 is definitely greater than 2. So now once we enter 5, it will automatically get arranged based on like the order, right? It will get arranged based on the order. So 2 is coming here. Now next, what is the next element? Next element is 3, right? So 3 will be added to the linked list. So 3 will be added to the linked list. 3 is removed from this part and here as well. And what is inserted? 4 is inserted. So 4 is inserted. So we come here and 4 is inserted into the priority queue. Now what is the next smaller element? See, 4 becomes the next smaller element, right? So 4 becomes the next smaller element, and we are sure that all other elements remaining are greater than 4, greater than equal to 4. So we'll add 4 to the linked list. We'll add 4 to the answer linked list, and we can remove 4 from here. We'll push the next of 4, so we'll remove it from here as well. So we'll push the next of 4, right? So we are coming here. Next of 4 is 4 again. So we are pushing 4 into the linked list, into the priority queue again. Now again, what is the smaller element? 4, right? So again, the next of it will be 4, and we'll remove 4 from the this. We'll remove this and we'll insert 5. So 5 becomes the next smaller element. So here 5 comes in, right? 5 comes in. Now what is the next smaller element? 5. So let's say this 5 is removed. So 5, one of the 5 is removed. So let's just remove 5 from the priority queue or the heap. 5 is removed from here, and we had 5 here, right? So 5 is removed from here, and we are coming to 6, and we are inserting 6 into the priority queue. 6, right? So similarly, the next smaller element will be 5 again. So like this, it will become the sorted linked list that we want, right? So it will become the sorted linked list. So what is the time complexity and the space complexity for this? Every time, what is the number of let's talk about the space complexity. Space complexity, initially we are inserting k elements, all the first nodes of each of the k linked lists. After that, every subsequent step, we are removing one element and we are inserting the next element in the linked list, right? So it is order of k. Order of k, the space complexity will be order of k. What about the time complexity? Time complexity will be, we are going through all the elements, and for every element we are actually searching on the priority queue, which is a log k, because the size of the priority queue is k, so it is log k for every element, and number of elements will be n into k, right? N into k into log k. So this is the total time complexity involved with the merging with this approach, right? Let me know if you have any doubts. Let me know if you have any doubts with this. So this is the total time complexity. This is the space complexity order of k. Now we can go towards writing the code for this. Right, it's pretty simple. There's nothing rocket science into this logic. Pretty simple problem. So let's try to write the code for this. Let's go full screen. Okay, this, right. Before we start, we have to create a min heap, right? So we have to create a comparator. So struct compare, let's call it a struct compare. And so let's call it compare, and bool compare. I think we write a comparator like this only for a priority queue. So struct node star a, b, and what will return? Will return a of data is greater than b of data to create a min heap out of this. So, and let's call it type def struct compare, and let's write here compare. I think we recreate a comparator like this only. So first of all, we'll create a priority queue. Also, we'll create node star head head equals to null, right? Initially, and we'll create a priority queue. Priority queue. What will be the type? It will store node star the container, and it will be greater, not greater actually. It will be compare, right? Compare pq. I believe we created like that only, right? Let me quickly check once. Okay, is my connection gone somehow? Okay, I think it's causing problems. So let me switch the internet quickly. Let it be. Let it be. Okay, anyways, we'll look into this later. So priority queue. Now what we'll do? Uh, we'll go through all the linked lists. First of all, we'll insert all the first key elements. So we'll go through the entire set of element, all of them. So I less than k, I plus plus, and pq dot insert pq dot insert arr arr I0, pq dot insert arr I0, and not pq dot empty while not pq dot empty. Also, let me just check quickly once. C++ priority queue comparator. I think we'll definitely find something here. So STL, and how do we create a comparator here? If we see compare height bool operator, okay, we bool operator, we are overloading on the operator, okay, bool operator, we are overloading on the operator. So let's write here operator. Uh, So we are basically overloading this operator with whatever we've written here. So while not pq.empty, what do we do? We'll take the first element. So node star current equals to pq.top and pq.pop, pq.pop, and then what we'll do? Uh, we'll insert the next element. So head. So if head equals to null, head equals to current, and also will maintain a node star current position equals to null, head equals to current, and so head equals to current and current position equals to current, right? Current position equals to current. Yep. Current position equals to current, and yes, else what do? We do current position of next equals to current position of next equals to current, the node that we have. Yeah, I think that's good enough. Current position of next equals to current. And are we losing the connection somehow? Like, will this cause problem anytime? Current of next. Let's see. So current position of next will be current, and current position equals to current position of next. We're going to the next node. Otherwise, we can create new nodes every time. We can definitely do that. But let's see if this works actually. I don't want to create new nodes every time. So current position head equals to null, and yeah, next what we'll do is we are just left with pq, and we are just left with inserting again. So pq dot push, pq dot insert, what do we insert? We insert current of next, right? we insert current of next we insert current of next. So that should be it. And also, if current of next is not null, definitely if current of next not equals to null, then we insert it, right? So I hope that this will work, because otherwise we can just create a new node every time. Here we are actually reusing the existing node only. We are using the existing node itself, but we can definitely try to create a new node out of them, right? So yeah, that should be it. Let me see the methods of priority queue quickly. So pq.push is there, and pop and top. Okay, q.push pop top. Okay, I think we have made a mistake. Top is there, pop is there, and it should be not insert, it should be push. So push pop top, push, and here also push, right? So let's compile and run. Let's see if this is working. Okay, push arri should be okay, arri should be the head pointer, right? So why are we pushing a 0 after that? It should be the head pointer, like all the elements should be arri should be the head pointer of that. So 1 2 3 4 5 5 6 7 8, and it is also expected. So I think that should be good enough for us. And okay, one more thing, we making something null? We are not making null, right? It might actually cause problem because of the null values, like the last elements next should be null. So let's do that as well here. So current position, wherever we are at, the next will be equals to null, right? The next should be equals to null. So let's run this again. Yeah, I think that should work. So let's submit. Okay, it has worked. So this is the code for, like, this is how we can solve merging case sorted linked list. I hope that the complexity is clear. Like, if you see into the complexity, first of all we are pushing k elements, and after that we are running